In this video, we are going to look at parametric equations. We'll look at how to sketch the graph of a parametric equation and how to eliminate the parameter in a pair of parametric equations. Up to now, we have focused on explicit equations of the form y equals f of x, such as this quadratic. And sometimes we've even looked at implicit equations, like the equation of this circle. However, it is sometimes useful to define an equation in terms of a third variable, usually t, to represent time. Thus, we talk about parametric equations of this form, where both x and y are functions of t over some time interval. The graph of a set of parametric equations with independent variable t is the set of all the points x and y that are traced out over the time interval from a to b. So that if you have a pair of equations that define x and y, that any time t will tell you where you're at in the coordinate plane. At the beginning of your time interval, we could find our coordinates by looking at f of a, g of a. And then as time goes from a to b, a curve will be traced out, giving us different ordered pairs, until we finally get to the ending point of our time interval, where we would be at the coordinates f of b, g of b. Let's look at an example. Let's sketch the graph of the parametric equations given here on the time intervals 0 to 4. To do so, we could plot a bunch of ordered pairs for convenient choices of t. Let's run through and pick some of our values here. If t is 0, then we plug into our x equation and we get what x would be a negative 3. And if t is 0, our y equation would give us negative 2. And so our curve would start at the ordered pair negative 3, negative 2 right here. And this would be at t equals 0. At t equals 1, we would calculate the next point that our curve goes through. And we would get the ordered pair negative 1, 1. And so after 1 second, our curve will be about right here. At t equals 2, we plug t equals 2 into our equations. We would get the ordered pair 1, 0, and we would be right here at t equals 2. At t equals 3, we would get the ordered pair 3, 1. And we'd be about right here on our curve. At t equals 4, we plug 4 into our equations. We'd get the ordered pair 5, 2. It would be about right here at t equals 4. And so that we see as time goes from 0 to 4, we trace out a curve that goes in this direction that we have here. We do observe that this looks a lot like a line, and we could reparameterize or eliminate the parameter t in our pair of equations to get an explicit equation of our line. One way to do this would be to take our first equation in x here and solve this for t, in which case you'd have x plus 3 all divided by 2 is what t is. It might be easier to rewrite this as 1/2 x plus 3/2 though. And think of this as a substitution we can make into our second equation for t. So that we would have y equals something that we would use for t minus 2. And let's stick in there our 1/2 x plus 3/2 that we found. And then rewrite this expression as 1/2 x. The 3/2 minus 2 is minus 1/2. Notice that this is the same line that we found already. It's a line with slope 1/2 and y-intercept at negative 1/2. Here are some other typical parametric equations and their graphs that we would like to recognize. All of these can be graphed by making a t-table and plotting a series of points that'll trace out our curve. However, oftentimes it is easier to eliminate the parameter t to come up with a more familiar form of our equations. We already saw in our last example that this first set of parametric equations, which defines this line segment, can be rewritten as y equals 1/2 x minus 1/2 by eliminating the parameter t. This same process can be done for these other pairs of parametric equations. Let's look at the second example now. To eliminate our parameter t, we could take our second equation and solve this for t. We would add the 1 to the other side to get a y plus 1, and then divide by 2 to get an expression for t that we can substitute into our first equation. So that we would have x equals some expression we'll plug in for t minus 3, where we're going to plug in here the y plus 1 divided by 2. Of course, we can rewrite this by distributing this exponent, this 2, as 1/4 y plus 1 squared minus 3, which we recognize as a parabola that opens to the right like this, with the vertex at the ordered pair -3, -1. Let's look at this last example now. That looks like it's defining a portion of an ellipse. Not the entire ellipse, but just the portion that would be described on the interval from 0 to 3 pi over 2. Of course, to find the more familiar form for the equation of this ellipse, we could solve these two equations for the cosine and the sine portion. For this first one, if we solve for cosine, we could write this as the cosine of t would be, well, we would subtract the 1 to the other side and then divide by that 3. And if we solve the second one for this sine expression, for the sine of t, we could write it as y divided by 2. And if we recall our fundamental unit circle identity, which says that the cosine squared of any angle alpha plus the sine squared of any angle alpha will always equal to 1, and use these as substitutions for the cosine and the sine, we could write this as x minus 1 divided by 3 squared plus the y divided by 2 squared equals 1. Of course, we would recognize this as the equation of an ellipse with a center at, well, this would be centered at 1, 0. It would have a major axis right here of 3 along the x direction, and a minor axis of 2 that goes in this y direction. Well, I hope this video is helpful, and I'll see you guys next time.